Okay, but let's finish up 4.3 first. 4.3, we finished up to the bottom of page 50 last time, did we not? Yes, we finished example 2, the bottom of page 50. And then I'm on top of page 51, where you have this little chart, which I recreated. I'm making sure I copied it right. Top of page 51. So that's a chart that has an assortment of students who go to an assortment of different types of schools and separated by which school they go to and their genders. So there are 8 females that go to community college. And there are 10 males that go to the university. So we've seen these charts before. By the way, a lot of times when you're doing probability questions, it's helpful to make one of these tables if they don't give you one. Sometimes they give you enough information that if you organize it into a table, it's actually easier to do the problems. So using that, I'm going to answer a few questions. And we're going to kind of focus on the conditional probability part. Conditional probability, remember, was the probability of some event happening given that you know another event has already occurred. I think my example last time was the probability of you getting to class on time given that your car doesn't start. Knowing that your car didn't start changes your probability. Is that the one I used last time? Okay, good. I'm trying to jog you my memory. Okay, so starts off nice and straightforward here. The first question is the probability, bless you, of choosing a male, a student who's male and in high school. If I look at all these people, how likely is it that if I select one person, I get a male who's in high school? I heard 7 out of what? Can you speak up back there, Kirsty? What do you say? 7 out of what?
7 out of 61.
7 out of 61? Where'd she get 61? She added them all up. We need to know what our total number of options is here. How many students do we really have to choose from? So let's double check her work. Not that I don't trust her, but double check that all of these numbers add up to 61. I see some people nodding. They do? So therefore, if I'm going to imagine, like this is kind of like the marble example I did. Imagine all of these people in a nice little bowl. I'm going to reach in, and I have 61 to choose from. So that's my denominator. How many of them are males who are in high school? 7. We could turn it to a decimal, but right now I'm more worried about setting it up. Did this and make anybody think of anything? I heard multiply up here. Is that what you're going to say too? Yeah, we said and always means multiply. I'm not sure I said always means multiply. But or was add and was multiply. The subtle difference here is that we're only selecting one person. The and is when you have one event followed by another one. So for example, if I wanted 2 males who were both in high school, the first one would have a probability of 7 out of 61, and the second one would have another probability, which would then be 6 out of 60. But the and, when you're doing 2 at a time, that's where that and comes in with the multiplication. If it's just 1, there's no other fraction to multiply by it, because there's just one guy. See the subtle difference there? Sometimes and just means they're in 2 categories, as opposed to this is going to happen and then that's going to happen. Okay, so that one wasn't so bad. The next one is very similar. Male, I'm going to write it slightly different, given that it's a high school student. Remember this notation from last time? That straight line means given. So this is read as probability that a person is male, given that we already know it's a high school student. So I picked somebody randomly and someone said, hey, by the way, the person's in high school. We already know that part. What do you think's going to happen? She thinks maybe they're going to be the same. What are you thinking over there? Maybe the denominator's going to change? Maybe, yes?
Is it all high school students?
So that's what we want to consider is all high school students and then talk about the males. What else did I hear over here? Was that you again, Kirsty?
Yeah.
Are you talking to yourself or me?
Kind of talking about
Do you want to tell me what you said or no? I just didn't hear you.
No, I'm just a little confused, so.
Oh, okay, you're talking to yourself, trying to figure it out. Does everyone agree that it looks similar to the first one? The subtle difference is, in here, I'm gonna reach in, grab a person, and hope that it's a person who's male and in high school. I might get a male who's not in high school, I might get a high school student who's not male, but I'm hoping that I get somebody who's both. That's what this one was. This one says I reached in there, someone says, oh, by the way, the person you got is in high school. We know that much. Now that we know that much, how likely is it that it's male? The subtle difference? Yes.
Would that be like 7 times 12 over the total high school students? I'm sorry, that'd be 7 over 12 high school students, which would be 19.
Exactly. So as soon as we knew this, as soon as we know the person's in high school, that means that I'm just looking at this part of the table. I know I'm only looking at those people if I know they're in high school. Everyone agree with that? So now that I know I'm only looking at these people, what's the probability of getting a male out of these people? 7 out of the total here, which is 19?
Yep, yep.
That makes sense? So you were totally right in your first guess back there, Kirsty, when you said, is the denominator gonna change? Yes, the denominator changed. Because this one is selecting a male who's in high school out of everybody. This is selecting a male just out of the high school students. Questions? A little note here. Total high school students. This one is total students. Now look at the next one. The probability of selecting a high school student given that it's a male. Make your head spin after a while because they all look the same.
So you add up all the males?
So she's saying out of all the males, she's
Yeah,
looking
and
here
then
saying,
it's like 7 divided
7
by
over
3.
it's a different denominator though now, right? Because as soon as I know I'm just looking at the males, I'm looking at, oh, everybody's all up, not quite. I'm looking at just that top row, right? I know I'm only looking at those people, and I hear people tell me those add up to 30. So the difference here is I'm starting looking at my 30 males, and now that I'm only looking at those 30, the probability that the person is male, is high school, there's 7 of those 30 that are in high school. So a lot of people think conditional probability is really hard because, well, how do I know what my denominator is? It keeps changing. I think it's fairly easy as long as you do something similar to what I just did, is cross off and look, cover up part of your table. It's just cover up and look at just the part that they want and then answer the question. And it's important that what comes second is the part that you're looking at as your denominator. Yes?
Why isn't it all high school students? Why is it just the males that we choose?
Because we know, right here, we know the person's male. We're only looking at males. So that's essentially telling me, assume that we don't even care about these people. We don't even know anything about them. If no one had ever told us about the females, it wouldn't matter, right? We're just saying, if we're looking at those males, we know that part. Out of those males, what's the probability of high school? Erase that right here. This down below. Other questions? Of course I make it look easy because I know what I'm doing, right? So that's why you want to ask questions if you're not 100% sure. But basically this conditional probability, let me erase this, I still need these numbers. Conditional probability changes your denominators. And it doesn't always say given that. It might say, what's the probability of selecting a male if we know that the person's in high school? So it might say if we know that. We actually had a conditional probability problem on that quiz. Did I ask you that one? Might have been the other question on it. The one about the doctors and the calculations. Oh no, the quiz, one on the quiz was not that. But there was one that said, of the people who got it correct, what was the probability that it was the ratio label? It was something like that. So it actually told you, just look at the correct ones and now find the probability. So it worded it a little bit differently. Okay with those first 3? Okay.
Does the second part usually, that's usually gonna be the denominator, right?
Yes. The second part, whatever was given, is gonna be the denominator.
Okay.
But my little warning just now was that it doesn't always come second, because it might be phrased in a sentence saying, if we know we've selected a high school student, what's the probability that he's male? So then it's written first, but it's always what you know, and what was given is your denominator.
Okay.
Other questions? Okay, so now what's going to happen is out of the same table up here, instead of selecting just one student, I want to select 4 students. So right below the middle of the page there, 4 students are selected. So now I'm selecting 4. And I want to find the probability that all are university students. What changes here? Everything. I don't think it's everything. A lot.
We assume that there isn't replacement, right?
Okay, so we're assuming there isn't replacement, because we're taking more than one person at a time here, and we always assume there's no replacement unless we're told otherwise. So we're going to select a person and not put them back in the group, and then select another person, and so forth.
We're gonna be concerned with the university students, the male and the female.
Hold that thought, Chrissy, what were you saying?
Maybe like 4
It wouldn't be 4 over 21. Chrissy, what were you saying?
I was saying that we would be focusing on the university students of male and female. What I did was I put 22 over 61.
I did.
21,
I
yeah.
think you could, that's a good starting point. I saw your hand too,
Well, that's
Kevin.
before separate events, right?
4 separate events, that goes back to what Evelyn was saying. She wanted to use the number 4.
That's before.
But remember, because it's 4 separate students, what does that tell us we're going to do?
if you
Do it 4 times.
4 different probabilities that get multiplied together. So I'm actually glad you were wrong on that, because it's a very common error. We even talked about that last time. Where do I put that 4? But we're not using the 4. We have to think of it as one at a time. We're going to select one student, and then select another one.
And then the second one would be like
21
1 out
over
of
61
20,
and 20.
and then 1 out of, because like the population goes down every time one is picked, right?
Yeah.
Yes,
the
but let's talk about where to start. So I'm gonna get a university, and then a university, and then a university, and then a university person. So there's a little shorthand for saying the probability that the first student's from the university and the second student's from the university, yes. Go ahead.
How do you know if it's gonna be like without replacement or?
We assume it's without replacement unless we're told otherwise. Because in real life, most of the times, if I needed to select 4 of you, I wouldn't pick you and then put you back in and try to pick somebody and get you again. It just doesn't make sense, right? So most of the time, we don't do things with replacement. There are times like when they're doing quality control things where they do things with replacement. They check one, they put it back in, they check another. But most of the time, we assume it's without. That's the default. So these were those hidden ands I talked about last time. Now, do we know anything in advance about this person that we want to be a university student?
No.
Do we know it's male? Do we know it's female? Do we know anything? So then what's my denominator?
61.
61, the first time I reach in to grab the student, right? Because there's 61 total. There's nothing that was given here. So for my first student, there are 61 students to choose from. And how many of them are from the university? 21? Adding these up? 21? And here's the and that tells me to multiply when I have more than one event. So now it's without replacement. So now there are only 20 university students out of 60 students left.
Yeah.
And then 19 out of 59 and 18 out of 58. Could I have used the shortcut here? The 5% rule for cumbersome calculations?
No.
Why not?
It's 5%.
No, 5%.
Yeah, 5%. I'm taking 4 out of 61 students. What is 4 out of 61? Could someone turn that to a decimal for me? 4 students out of 61.
0.066.
which is approximately 6.6%. It's higher than 5%, so I can't use the shortcut. Remember that shortcut's only when you're taking a few out of a giant population. My population is not giant to begin with, and I'm taking a few too many. Yes?
I have a question about that shortcut.
Uh-huh.
Would you just, use the first fraction for the shortcut?
Yes. So if I was taking a small enough number out that this was less than 5%, I would just take the first fraction and multiply itself 4 times. So I would just write 21 over 61 times 21 over 61, or raise it to the 4th power. That's the nice shortcut, but only when you're taking a few out of a large population. Good questions. I'm not worried about what this answer is right now. I know we could all multiply. I'm more interested in setting them up for you. Is everyone okay with that? I'll figure out what they are later and tell you the answers after the break, maybe. But it's the setting up. What'd you say?
I just thought it was funny.
Oh. People really want to know. I'm like, you know how to use your calculator. And if this was an exam question, let's say this was an exam question, and you set this all up, and you put the wrong answer over here, I'd probably give you 9 out of 10 points. Because setting it up is the hard part. The only reason you'd get less than 9 is if you gave me an answer higher than 1. Why would I give you less than 9 points then?
Because you know it can't be higher.
Because probabilities cannot be higher than 1. So you're telling me you don't even understand probabilities if you did that. But if you punched in your calculator and got the wrong decimal, but it still could have been a probability, I'm not so worried about that as I am that you know how to set it up. Okay with that one? Yes?
Are these videos that you're making posted online already so that we can rewatch them?
No, we're having an issue with the software. We need to edit them, so none of them are available yet. Sorry. We're supposed to be getting that software any second now. When it does get here, I have to start editing from the beginning. Actually, maybe I'll start editing backwards so that the more recent ones are available for you guys. But we are still fighting with getting the software, and so I can't edit any of them.
Okay.
So the goal was to have them going right away. But life doesn't always go the way you want. But I'm glad you asked to make me think of doing them in reverse. Okay, that was all for university. So the next one is the probability that none are from the university. I'm going to erase this little part right here. Probability that none are from the university. Better be careful here. Describe to me these students one at a time.
So would that be 40 over 61?
That'd be the first one, yes. How did you get 40 out of 61?
You added everybody that wasn't?
Everybody who's not from the university. So she's trying to find how likely is it that I grab someone who's not from the university. And then the next person would not be from the university, and the next one would be not, and so forth. So let me actually write that out before I go with what you started there, Hannah. Not university. Ooh, actually, I'm going to use some different notation here. University complement. You guys okay with this notation? What do I mean by that?
Compliment?
Complement, not university, right? That's what that means. The first person's not from the university, the next one's not from the university, the next one's not university. It's a shorthand for writing not university.
So would you just subtract one like you did to the top one?
So we would just subtract, we come over here and say, okay, well, there were 21 that were in the university. All of these people are not in the university. So you could either add them up, which is 40, or you could subtract this 21 from the total, and you still would have 40 that are not in the university. So if I'm going to reach in and grab one student, I still have 61 to begin with to choose from. We all agree there's 40 who are not in the university? And I have to grab another one. How many students are left? I heard 39 out of 60. There's 60 students left. 39 left who are not university students.
And 38 over 59.
And then 38 out of 59.
37 out of 50.
And 37 out of 58. There's a lot going on in this one problem though. With me talking you through it's a little bit nicer. But you have to stop and think, okay, if I want 4 students and none of them go from the university, the first thing I have to do is think about these people one at a time. The first one, the second one. So that's the first part, is knowing I have to multiply my 4 fractions. And then you have to say, okay, for each fraction, what am I doing? I'm looking at the total and asking myself, how many people are not in the university? And then, of course, the totals changed as we went along. Questions there? Okay, last one. Probability that at least one of the four, at least, let's put an L in it, at least one of those four is from the university. Yes, ma'am.
Are you not gonna like get them, are you not gonna solve them?
I wasn't going to, but I'm going to need to actually do this problem. We'll talk about why in a second. We'll do them all at the end maybe, because I need part of it right now. So when you see that at least one, who remembers the little words that we saw last time that should send little bells and whistles off in your head? The complement. Every time you see at least one, you want to consider the complement. Because at least one is hard. You have to consider, well, what if it's exactly one from the university? Or maybe it's exactly two from the university. Or it's three. Or it's all four. There's so many different ways to have at least one. What's the complement of at least one being from the university? None are from the university, right? Either at least one or none. So this is going to equal 1 minus the probability of none from the university. Recognizing that at least one, let me get my color here. Recognizing that at least one, and knowing that it tells you to do 1 minus the probability of none is huge. The extra credit quiz I mentioned earlier is using the same idea today. There's problems on your online homework doing that. There's ones on the exam just like this. Is everyone all right with why I wrote that? I claim that we already did part of it. We just didn't multiply it out. The probability that none are from the university is what we just did right here. Right? We did none are from the university, which is why Hannah was saying, are you going to multiply this out? Maybe we better stop and multiply this out because we need to know what that number is. Can somebody multiply that for me? See what we get? We'll do the other one too.
0.1751?
This one?
Yeah.
Let's wait and see if someone agrees.
That's
Are
what
we
I got.
rounding it?
Let's round it to 4 decimal places. It'd be a 0? I got a 1 or a 0? Will someone break the tie here? You got a 1?
Well, it's one, but if you round it, it'd be 0. I think.
Well,
you're-
you won't ever round down though.
Oh, well, if it's.
If anything, we would go up to a 2.
Okay.
It's one.
Oh, maybe you're rounding to 3 decimal places. I want to leave it at 4 decimal places.
It's 0.175.
That's what I got.
Yeah, it's 175.
So the only reason this would be a 0 right here is if this was a 0 and then there's some of the numbers after it.
So we usually do 4 or 3?
It depends on what you're at. I just decided to keep 4 since the first number I heard was 4. If we wanted to go to 3, it'd be 0.175. Right?
That's what I wrote down.
That's fine. If I don't tell you where I want you to round, then I'll take either one. On a web, not website, My Stat Lab, they tell you exactly where they want you to round. So how would I finish this problem then?
Subtracted by 1.
Just subtract 1 minus that, right? 1 minus 0.1751,
0.8249.
8249. There's around an 82% chance that if I select 4 people, at least one of them is from the university. Pretty likely that's going to happen. Let's go ahead and figure out this one while we're here, since we skipped over that one too. Anybody get this one for me? Or- Go ahead. Wait,
0115.
0115? Is that what I heard?
Yeah.
Someone agree with her?
Yep.
Yeah? That's a very small probability. It's less than 0.05, which means it's unlikely. It's unlikely to get 4 students all from the university. Hard to do. There's so many people from other places too. You get one, that's not a big deal, or maybe two, but all four of them? Hard to do. Questions? So here's the tricky part. This question right here could have been the only one I asked. Maybe I didn't give you the information leading up to it. We didn't start by looking at little things one at a time. We didn't build up by doing these 4 multiplication problems. This could have been the only one that I asked. Would we have had enough information to do it?
Yeah.
Yes, because what would it have looked like if I was doing this problem from scratch, if I wanted to set it up? Because I just kind of stuck this number in there that came
You
from
just have to
earlier.
include that.
I would have to include this part. So I still would have written out 1 minus the probability of none. And then I would have had to figure out the none over here. I would have had to put the 40 over 61, 39 over 60, 38 over 59, and the 37 over 58. So this is 1 minus, and then I would have had to figure out the probability of none if I hadn't already asked us to do that. And then this would give us the same answer. Questions? So I'm gonna guess you're gonna have a few questions here, because now I'm gonna give you your extra credit quiz.
So when you see that, at least one, that's a factor that you're gonna have your equation, that's gonna be 1 minus something else.
1 minus the probability of the complement,
Right,
yes.
so those two are gonna add up to 1.
Mhm.
Right. So you're gonna have something that's gonna add up to 1.
Right,
So it's gotta be 2 different problems.
yes. It's, you have to figure out that none part,
Right,
and you have to know to take 1 minus that to get your original problem.
right.
There's a lot of these problems that have like 2 or 3 or 4 different parts in them that you
Almost
have
like
to.
algebra.
Yes, and you have to really think about each piece. Other questions? And it says 4.4 counting, if you change it to a 4.4 counting. The very first thing I want you to do, if you didn't do it already, is it should say the multiplication counting rule.
Where it says fundamental.
Where it says fundamental, this says multiplication. It's the same thing, but they changed the terminology, so if you're like trying to do it online and they ask you, they refer to this rule, they have a slightly different name now. So, let's read what the rule says. If one event can occur in m ways, and another event can occur in n ways, then the events can occur together in m times n ways. Okay, whatever the heck that means. Let's look at example 1 and then we'll go back and read it again. Example 1 is the same example we've done now for a couple days in a row about flipping the coin and then guessing on that multiple choice question. Remember we were doing that last week, I think it was? Where you flipped a coin and you had 2 options, heads or tails, and then you had to guess on the multiple choice question and you had 5 options there. Remember our sample space that we made for that? How many things were in that sample space? There were 10. We had heads with all the 5 options and tails with all the 5 options. Heads A, heads B, heads C. If you look back at your notes, there were 10 of them there. So there were 10 different possible outcomes. What the rule is trying to say is there were, for the coin, there were 2 outcomes. For the question, the multiple choice question, there were 5 options. And so the total number of outcomes that could have happened was 2 times 5, which is 10. Yes,
It doesn't work with the boy-girl question too?
the boy-girl question.
Like, assuming the probability of getting a girl and boy are equal to each other.
Oh, yes, yeah. So like it was a family that had 5 kids we
Yeah.
talked about, and I said there would be 32 things in our sample space if we wanted to list them all. So if a family has 5 kids, how many different outcomes could there be for the first kid? 2, it's a boy or a girl, right? And the next one, there's 2, and the next one, there's 2, and the next one, there's 2, up to 5 kids.
So 2 to the 5th power?
2 to the 5th power, which is 32. Which means that if we had made a sample space for all the ways that someone could have 5 children, all the boys, girls, first one's a boy, the other ones are girls, that's how many different things would have been in our sample space. So this is yet another way to find probabilities without having to list your giant sample space, because it takes too much room and there's too many places to make mistakes. And what are you gonna do when there's a billion things in your sample space, right? So that's what that's saying if you go back and read the rule now. If one event can occur in 2 ways, and the other event can occur in 5 ways, then together they can occur in 2 times 5 or 10 ways. That's all that's saying. We've actually kind of been doing that already. Okay with that?
So that's the answer?
Yeah, that's the answer, 10. There's 10 outcomes. Number of outcomes is 10.
Easy.
Mhm.
This one is easy.
So what we're doing now is finding a new way to calculate our denominators for how many different possibilities are there. So let's look at example 2. How many possible 9-digit social security numbers are there? Assuming that, I don't know the rules about social security numbers. You can start with zeros, you can, the numbers can repeat, whatever. There's no special rules about it. There's 9-digit numbers. How many different 9-digit numbers are there? 9? 81. Here's a little space for my 9-digit number. You guys are gonna try to guess my social security number. I'm so glad you're laughing. That means you know what the heck I'm talking about. There's a dash here and then a dash here, right? So I want you to guess my social security number.
This one, 90? 1, 2, 3, 4, 5,
It's a
6,
lot
7,
more
8,
than 90. 1, 2, 3, 4, 5, 6, 7, 8, 9, she says.
Well, there's
Wrong.
11 different numbers, right?
There's 9.
There's 9 different
From
numbers.
10 is 0 to 10.
Oh,
I
so-
guess you don't use 10, right?
Oh, so when I go to pick the first digit, I like the way he's thinking. When I go to pick the first digit only, I just want you to guess the first number. How many different options do you have?
9.
Count to 0.
Yeah.
0 through 9 is actually 10 options?
10, yeah.
Do you agree there's 10 different things you could choose here?
Yes.
Same with every number.
And there's 10 different numbers you could choose here.
All of them are 10.
And they're all 10, right? Let me change my dash into
Oh,
multiplication.
they're multiplying.
And we're multiplying them because there's the first digit and the second digit and the third digit and the fourth digit.
So 10.
Oh my God, there's
10
a
to
lot
the
of
9th
zeros.
power.
There's a lot of zeros. 10 to the 9th. It's a 1 with 9 zeros.
Yeah.
That's 1 billion.
Ooh, I like that.
There's 1 billion different social security numbers to choose from. So that's the first part. How many possible 9-digit social security numbers are there? There's a billion. What is the probability that you're going to guess mine?
0.
Very, very.
It's not 0. Somebody could guess mine. I have one. I do have one.
Is it 1 out of a billion?
Aha. She says, is it 1 out of a billion?
Because it has to happen, right?
Yeah, because there's a billion different possibilities. Put my commas in here to make sure I have them all in there. That's how many different social security numbers there are. And how many of them are mine? Only 1. There's a 1 in a billion chance that you're going to guess it, which is why you all laughed when I asked you to guess it. Because it's not impossible, but it's extremely unlikely that you would guess my social security number. When you're doing these problems online, it'll actually ask for your answer as a fraction. Because if you turn it into a decimal, it gives you like e to the negative 8 or 9 or whatever. It's so small that it puts it scientific notation. So there's a reason they ask for you to leave it as a fraction, to show that you know what that denominator is. So don't spend too much time guessing. I wonder how long it would even take to guess a billion social security numbers. A long time.
How many guesses do you get done?
How many can you do in a day? Let's see if we can start figuring that out. Okay, so now in the middle of the page, how many different ways can we arrange the following letters, X, Y, and Z?
9.
9, I'm hearing?
Yeah.
3 times 3.
I say
6?
9.
X, Y, and Z. I heard 9, I heard 6. Well, there's one arrangement. Maybe we better list them. It's only 6 or 9 if somebody in here is right.
9.
What's another way I could rearrange them?
ZXY.
ZXY,
X is equal.
XZY,
YXZ.
YZX. Nobody's repeated any yet. We gotta run out eventually.
ZYX.
ZYX.
There's no XYZ.
That's the first one, I left it up here. XYZ.
Is that it?
1 by 6.
Is that it? Anybody come up with another one that we missed? Anyone that you're coming up with, I bet's already up there. So there's 6. Okay, that's nice, but what if there were a whole like 5 or 10 letters that we wouldn't want to list them all, right? So let's talk about how the counting rule actually would have given us this 6. We all agree there's 6 of them here?
Yes.
When I tell you to choose the first letter, how many letters do you have to choose from for the first one? 3. Now that you chose the first one, say you chose Y,
Oh.
how many do you have left to choose from?
2,
Then you only have 2 to choose from,
and then 1.
and then you have 1 left.
That makes sense.
So there's 3 to choose from for the first letter, but then there's only 2, and then there's only 1 after that. And if you multiply those out, there's 6. So we actually were doing the multiplication rule there when we calculated 6 of them. This just verified it. So we're still doing that. There's 3 to choose from. This is because it's like without replacement, when we're not repeating. That's why the numbers went down. And this notation comes up so often that we have some mathematical notation for it. It's called a factorial. See right underneath there it says factorials. There's 3 with an exclamation mark. It's not like 3, yay, we love 3, it's our favorite number. 3 with an exclamation mark, we read that as 3 factorial, actually means start with 3, bless you, and multiply every number less than that until you get down to 1. So in this case, the answer was 6. I'm sorry?
Oh, I said the excited 3.
The excited 3 is really 3 factorial, yes.
So now, like, in your calculators, there's like a,
Mhm.
can I get to that?
Yeah, I'm about to get there in like less than 2 minutes. She says she knows her calculator's gonna do it. Because see the 10 factorial coming up? I don't wanna do it in my hand either. Let's do 5 factorial next. What does that mean?
5 times 4 times
5 times 4 times 3 times 2 times 1? It means start at that number and keep subtracting 1 and multiply until you get down to 1. So if we multiplied this out, 5 times 4 is 20, times 3 is 60, 60 times 2 is 120. But when we get to 10, that's a lot. Some of you could actually probably get there faster than finding it on your calculator, but I'm going to show us how to find it anyhow. You have to multiply all that. There is a factorial button on our calculator, and the directions are right underneath those examples there. So you're going to go to Math and PRB. I'm going to show it to you up here because we're going to use that again in a second. Turn this on. Let's see if we can get the 10 factorial one. So, this is going to start up here. Can you get those lights for a second, please? Turn them back on here in a minute. Okay, so on your calculator, over here, the third button down, it says math. I know you can't see your calculator now. We'll turn the lights on here in a second. See where it says math? When I do math, and then there's all these words across the top up here. Mine says PROB. The old calculators just say PRB. We're going to move over to where it says PROB. And there's the little factorial sign right there. See it? Number 4? The problem is I have to type the number first. So I'm going to actually quit out of here. I'm trying to find 10 factorial. So first I'm going to type in the 10. And then I'm going to go into math. Come over here to probability. Knows we're working on probability. Come down here to the number 4 and hit this. So now it actually looks like 10 factorial, the excited 10. If I hit enter now, there's my answer. 3,628,800. Everyone okay how I found that?
Yeah.
Can you get the lights again, please? Thank you. So if you have anything really much bigger than 5, your calculator is probably a faster way to multiply than to write them all out. So in this case, I forgot what it was. What was it? 3,8.
3,628,800.
Jeez, just hold on for a minute. Okay. So everyone okay with that? Not too hard to find? Notice what it says there about 0 factorial. Type that into your calculator, 0 factorial. It tells you it's 1, which makes no sense. You're like, you're multiplying by 0. How can it be 1? It has to do with the mathematics of where factorials originally came from and how you set things up. Similar to, you know, when you had an exponent of 0, something equaled 1, those zeros have all those special rules. So if you ever end up with a 0 factorial, it will equal 1. For most of us, we won't because we're talking about probabilities and we're not going to have 0 items. So it's not going to even end up with a 0 factorial. But the factorial rule at the bottom is really nice. A collection of n different items can be arranged in n factorial different ways. So remember we started with these 3 letters? And the question was, how many ways can we rearrange them? And the answer was 3 factorial. So if I had 10 letters, like A through J, and I asked you, how many different ways could we rearrange these 10 letters? If I had 10 letters, A through J, how many of these would you come up with if you were rearranging the letters A through J? This number, right? We don't want to list all those 3,628,800 different ways to arrange those letters. But at least we would know how many different possible things could happen, and then if we were looking for the one that happened to have them in alphabetical order, there would be only one of those out of the 3 million and some change. So anytime you're rearranging things, that's where the factorials come. Okay, page 55. Another thing we think about is something called permutations. Permutations, it's still about rearranging things. That's why it talks about order matters in bold up there. And it's when you, oh yes, go ahead.
Can factorial be used on fractions? So
Yes.
like when we were doing, like earlier, where we had like, without replacement, we use that,
Yes, exactly.
I had in there.
Yeah, as the numbers were going down, right, That's actually where they came from. They happen so often that they gave them a nice little notation for it.
That's cool.
Okay, so the permutations at the top of page 55 is the number of permutations, things where order matters, when you're selecting R items from n available. Let's read example 3 to talk about what that means first. So let's say there's 38 of you in here. How many different ways can we select a president, a vice president, and a secretary of our class? So we're selecting 3 out of our 38. 3 people? Okay? And the question is, how many different ways can we do this? Now, we want to be careful because the order matters. Because let's say by chance I happen to get these 3 people right here when I pick 3 out of all of you. It's different if she's the president, he's the vice president, and she's the secretary, than if I go the other way around. Maybe Sarah wants to be the president, and he's okay being vice president still, and she's the secretary. We agree those are different permutations of the same people. Permutations are when you have the same group, but you can rearrange them and it means something different. Where if I just said I need to select 3 people to go to a conference for us, to represent us, these 3 people are those 3 people. They can stand in line however they want, but they're the same 3 people. But because I gave them positions, the order matters. I like to think of, because we're going to talk about combinations here in a second, permutations have to do with when you need to select order matters. Think of my example of when you need a president. P for permutations, P for president. Helps you remember which one is which. The order matters, you can line them up in some way. So if you want to find this probability, or excuse me, this number of different ways that we can do that, what we're saying in this notation at the top of the page there, let me get rid of this, Anybody get my social security number yet? Just wondering. Equifax gave it away already anyhow. 38P3. This is the notation for what this question is asking in example 3. It's saying, how many ways out of 38 people can we select 3 where the order matters? And the order matters because I'm giving everybody a title and they're going to fight over who's the president of these 3. Okay with that notation? So there's a formula there. The formula says that this is N and this is R. So the formula says that in our case, it's going to be 38 factorial divided by 38 minus 3 factorial. See how I'm following that formula at the top of page 55? So that's 38 factorial divided by 35 factorial. Let's see where those numbers came from. Use your calculator, please, and tell me what that equals. 50,616?
Yep.
Wait,
5616.
never mind. No,
You're not confused? You are confused?
I am confused. Wait, let me just try this first.
Okay, try it and see if you're confused. Does your hand over here? Oh, you're just stretching. Yes. Yes, there is a shortcut on our calculator to do permutations, but first we're going to do the factorials. You're asking about the factorials or the other way? Okay, the other way, we're gonna get there. Let's see if Hannah caught up with us yet. Did you get there? Are you still punching it in?
How do you put it in your calculator?
You'd have to do 38 and go in and get the exclamation mark,
Okay.
and then divide it by 35 and go in and get another exclamation mark.
Hit balance.
And then hit enter.
And then, it's, on mine it's number 4. It's the exclamation point.
Or some of you have just read ahead. There's a NPR button in your calculator. So you could do it this way, which is a little bit time consuming, less to do it in by hand, I'll argue. But there is a permutation button in the same place. Which one is it? Looking down the list, I don't have my calculator open. Number 2 says NPR in the same place under math and probability. You guys all see it there? So if we want to use that button, all we have to do is first type 38, go in there and do NPR, and then do 3, and then hit enter. And we should get the same answer. You may use this button on a test to find these numbers. You just need to tell me that that's what you did. If you just say, I'm trying to find 38P3 and the answer is that, I'm fine with that. I'm assuming you put it in your calculator. The important part here is that you knew it was permutations because the order mattered. Ask me a question, Kevin. I hear you muttering to yourself back there. Must be a question. What's the question?
I'm trying to put it in my calculator.
First you type the 38, then you go into math and probability and find this NPR button,
Number 2.
and then you hit 3 and then enter.
So that would be like the answer that we would get right here.
Yeah,
Okay.
that's the same answer.
Okay.
That's what I'm saying. So you can either do it this way, and you would get 50,616, or you could do it this way, and you would get exactly the same answer. Your calculator's doing the factorial work for you.
Okay.
Oh,
You
wow.
got it now too?
Yeah, I got it.
So that's
Thank
when
you.
we do permutations, when the order matters. Now, before we talk about combinations, look at example 4. How many different ways can we select 3 people to represent us at a meeting? Can you pull that door closed, please? Thank you. So what's different here? We just want 3 people to represent us at a meeting.
The orders matter.
The order doesn't matter. We just need a group of 3 people. And if it happens to be the same 3 again, there's no other group besides the 3 of them. I can't rearrange them and they don't become a new group, right? Order doesn't matter. So committee, if you just need a committee to go represent us, committee to me starts with a C and that tells you that you want combinations. Combinations is when order doesn't matter. The formula is slightly different. Example 4.
So we got another button already here.
Another button on your calculator, right. So there's a formula which you can use if you want. Or you can use the one on your calculator, which I do too, because it's quicker. This one is a messier formula. The only thing that's different here is it's NCR and 3. Same numbers, but this tells me order didn't matter. This one told me that order did matter. So if you never use that formula, I don't care. I'd rather use your calculator. Less chances for mistakes.
Then you
Yes.
go down to NC.
I got a smaller number than NPR.
Uh-huh. I'm glad you did. Let's talk about that in a second. He says he got a smaller number here. We'll talk about why it's smaller here once we get it.
8436.
Yep.
8436?
Yay.
Does it make sense?
No, because like if order doesn't matter, then we should get more numbers, right?
Ah, so let's talk about this. So let's say that I want to select a group of 3 of you. The chances that I happen to get these 3 people are 1 out of those 8,436. We agree with that? There's 1 out of 8,000. This is one group out of the
Or
8,436.
combination out of.
But if I now said that order matters, there's so many more options because not only are they just one group, but I can rearrange them. President, vice president, secretary. So there should be more options here
There's more choices.
because there's more choices. Because the group of 3 could be, I mean, there are really 6 groups, right? Think of this as the 3 people. President, vice president, secretary, president. There's 6 options for each group.
It's almost like a combination plate of the Mexican.
Guess what happens if you multiply this by 6?
It equals that.
It should equal the other one. Because for each group, there's 6 ways to rearrange them. So that's what it's doing, it's taking that into consideration. So the combinations should always be less than permutations. Because there's more options when you rearrange people. Yes.
So is it fair to say that the NPR is more specific to the, like, the grouping of like order and things like that, whereas the NCR is just more of a blanket question?
Yeah, I like that. NPR is specific where order matters, and it's just a blanket group with no details in the group when you're looking at combinations. I like that. Other questions? Okay, we ready to play the lottery? We'll play the lottery, maybe we're gonna win.
Is real money involved?
What'd you say?
I said, is real money involved?
No. Darn, no real money. Okay, example 5. The California Fantasy 5 lottery jackpot is paid when the correct 5 numbers are chosen from the numbers 1 through 39. What they don't tell you is that you can't repeat numbers. Like, so if you have the numbers 1 through 39, you have to pick 5 different numbers. You can't pick 14, 14, 14, and 14 every time.
So you gotta figure out what formula to use on these
Yes.
problems. So the first one I would use NCR.
So we have to pick 5 numbers out of 1 through 39, and then the question is, does the order matter when you play the lottery?
Well, yeah.
Not everyone plays lottery, so we may not all know, so I should give you some more details here. Typically, in the lottery, you get the right numbers, you win.
Doesn't matter what order.
Doesn't matter the order. They'll list them on your ticket even in numerical order from smallest to biggest. But when they actually get the numbers, I don't know if any of you ever watched it on TV or the internet. There's like it's like bingo, and there's this big thing with all the balls floating around in it, and they pull them out one at a time. So the first number might be 47, and the next number might be 2. But if you have 2 and 47 on your list, they don't care which order they're in, as long as you have those numbers. So for the lottery, it's without replacement, which is what we always assume anyhow. And that you can't repeat numbers, and the order does not matter. So add that to the end of the problem, because if you don't know the lottery very well, you wouldn't necessarily have known that. Typically, every lottery is that way. As long as you get the numbers, you're gonna win. Hard enough to get them. So the question says, find the probability of winning the jackpot the very first time you play. All right. What do I need to know? What do I need to know?
How many numbers they pick.
I heard you at the same time. What? Go ahead, Christian. What'd
Well,
you
how many
say?
numbers they pick, individual numbers they pick out.
Yeah, we're picking 5 numbers. What were you saying, Christian?
What, N and R?
Yeah, we need to know how many different combinations of numbers are possible. If you get to choose 5 numbers out of 39 options, how many different combinations are possible? Everyone agree we need to know that? I'm gonna write that out. We need to know I even used the word. How did I know it was combinations? I used the word combinations just in speaking about them,
Because
Because
the
there's
order
no
doesn't
order.
matter.
because the order doesn't matter. So how am I gonna figure out how many possible lottery combinations are even possible? Yeah.
You do 39 as you do the 39 and then the NCR and then 5?
Do we agree with her? There's 39 numbers to choose from. We're gonna pick 5 out of that group. And we wanna know how many different combinations there are. Order doesn't matter, which is why we're using NCR.
And you get 57, 57, 57.
There's 57, 57, 57. There's about 575,000 different ways that you could pick these numbers. So you're gonna pick your favorite numbers, 5 numbers between 1 and 39, and I'm gonna pick my favorite numbers. And if we all picked, there's 575,000 plus different ways we could choose our numbers. What's the question asking for?
The probability.
The probability of winning.
The first time you play?
The first time you play. So I played once.
1 over 5, 7, 5, 7, 5,
Yeah.
7.
Why is it 1 over?
The first time you have to play it is once.
These are all the different combinations that are possible. There's only one winning combination. There's only one winning combination. This is how many possible combinations. You see that? Questions? Okay, what about part B?
NPR.
Do the same, but NPR.
You guys are saying the same thing, you're both saying NPR? Because now it says, find the probability of guessing them in the exact order. How likely is it that you actually pick them in the right order? The only thing that's different, what I would have, was it 39? 39. And order matters now with the 5. There's still only one winning combination. But there should be a lot more options now, going back to Hector's earlier, because rearranging them so many different ways, there should be a lot more options. Go ahead, what were you gonna say?
6, 9, 9, 0, 8, 4, 0.
Is that what I heard? There's like 69 million different ways you could choose those numbers in a certain order. So the chances of you getting them in the right order are really slim. Hard enough to get the right combination. Really hard to get them in the same order that they come out in. Technically, the lottery does not care about the order. We're just practicing. Questions? There's quite a few problems on this lab assignment asking you about combinations and permutations, and you have to kind of think a little bit to decide if order matters or not. It's not always obvious. You may have to discuss it with your neighbor, the math lab staff. Yes, sir.
I messed on the other page. What should you write down for the factorial rule?
Oh, it's just, the rule is the rule. There's nothing to write down.
No, that's just.
That's just what we did, yeah. There's nothing to write down. Just point out that that's where we used that, we did the 3 factorial. Yes, ma'am?
I don't have a lab for.
Oh, I'm glad you pointed that out. The lab for 4.4 is connected to 5.1.
It's halfway down the second page.
On page, it starts on page 59. Oh, no, sorry, it starts on 58. Sorry, and it ends on 59. 4.4 lab, pages 58 and 59. Glad you noticed that. I'll see you guys on Wednesday. Or in the lab, whichever comes sooner.